TCP is such a common protocol, we use it all the time. When we browse the web using HTTP, or when we send an email using SMTP, copy files to a remote server using FTP, and even behind the scenes when a DNS zone transfer occurs. We take advantage of TCP's benefits such as reliability, flow control, and stateful connectivity all the time. These features make use of the fields inside the TCP header to establish a connection using SYN and ACK bits. TCP gracefully closes a session using the FIN bit, and its 16-bit window size helps control congestion. TCP connectivity starts with a three-way handshake, and each segment is sequenced and acknowledged during the session to ensure that we don't lose any data along the way. If so, we simply resend what hasn't been acknowledged. But the workings of TCP are also target for attack. These attacks vary in purpose and functionality. Let's look at three vulnerabilities. 1. The TCP SYN flood. 2. TCP session hijacking. And 3. TCP reset attacks. In a TCP SYN flood attack, there are three approaches that an attacker can take. There is the direct attack, there's a spoofing-based attack, and there is a distributed attack. In our example here, we can assume that our server is running HTTP. And so there is a daemon running, and it is listening on TCP port 80 for HTTP requests. When our host wants to view the web page being served, it sends a TCP connect message first. We perform the three-way handshake, and once established, the server can go ahead and deliver that content back to the end user. When the three-way handshake does not complete, this connection is considered half open. The server has to allocate resources to maintain and track the state of the connection, and this data structure is of finite size. In a direct attack, the source host uses its real IP address, and it sends a high number of connect messages to the server in an attempt to consume resources. But what's to stop the host from completing the handshake? Well, a firewall can be placed in the path to block the responses that are coming back from the host. Because of what's involved in making this happen, the direct attack is not the most common type of attack. Now in our next attack, our host becomes an attacker by sending a high number of TCP SYN messages to our server using a spoofed address. That spoofed address is either a non-existent address or an address that will be unreachable from the server. So when the server replies back, it goes off into nowhere, and that allocated memory is consumed and unusable. If enough of these requests are made, then eventually the server runs out of memory resources and can't service real hosts. Initiating attacks from a legitimate source address is a quick way to be located and shut down, and that's why spoofing is so common. So direct attacks, not really a popular method for attackers. Today it is more common to have either a spoofed attack or even a distributed attack among multiple devices that can be controlled by a single attacker. This is a scenario known as a botnet or a droid army. In this case, what happens is an attacker has control of multiple devices that are infected with some type of software, malware, that gives access to this command and control device. That device can then go ahead and send an instruction telling all of these devices to send TCP SYN messages at the same time to the machine, and can either spoof, again, a non-existent address so that the server never hears back, or again, a firewall could be in place in between so that the responses are never allowed to come back from the actual host addresses. But again, it's more common that you're going to see spoofed addresses that are non-existent. In any case, all three of these examples, the direct attack, the spoofing-based attack, and the distributed attack, are designed to consume each block of memory on that server, all of the server's resources, so that it's not able to service real requests. Well, another type of attack that we see is called a TCP session hijacking attack. Now you might recall that in a three-way handshake, we have something called an initial sequence number, an ISN. And in this Wireshark output, we can see the SYN, SYNAC, and ACK all taking place. And the initial sequence number, that ISN, is set to a value of 0. So our client, who's establishing a connection to the server, sets that value to 0. And the ACK that's going to come back from the server is going to be the ISN plus 1. So the ACK that comes back is going to be a value of 1. Now to complete that three-way handshake, this client needs to send an ACK back. And the sequence number at this point is going to be a value of 1. And so this is how the sequence numbering works. Now, in a TCP session hijacking attack, the goal of the attacker is to guess the ISN and then ACK the last TCP segment of the three-way handshake. Now this is known as a blind TCP spoofing attack because the attacker has to guess what the ISN is. In other words, the attacker doesn't see the packets as they cross the network. He's not connected, he's not in the path, he's not able to see those packets. If he were able to see those packets, meaning that attacker is somewhere sitting on the network and he has perhaps Wireshark open and he's able to capture packets, well, in that case, TCP session hijacking would be the non-blind type of TCP session hijacking. He doesn't need to guess because he can see the traffic that's there. Well, this is just another example of what can happen on a network. Now, some common tools that are used for session hijacking, we have Juggernaut, we have Hunt, we have TTY Watcher, and we have T-Site. Some of these tools you'll find made available to you in Linux distributions like Kali Linux, which is of course common for penetration testing, but it is definitely something that we want to be aware of. Now our final TCP attack is the TCP reset attack. Now assuming that two TCP hosts are talking to each other, an attacker can disrupt communications by sending a TCP reset to either party in the session. And this attack mainly disrupts communication between two endpoints. But let's look at how a standard TCP connection should close. So what we see here is a host who is talking to a server, and the host has just received some data. And now the host is finished with the connection. So he's going to send a TCP segment, and in the flags portion of the header, he's going to toggle the FIN bit. Now when the server receives that, it's an indication to the server that the connection is finished. The server will send two messages back, an ACK as well as his own FIN, and that FIN needs to be ACKed by the client. In this case, it indicates that the session is now closed, and we have done it in a clean fashion. Now there's another way to close a TCP session, and that's using the reset bit that we find in the TCP header. Now normally that value is 0. We don't do a reset if we see a value of 0. And so everything operates normally. But if we toggle that bit, it indicates that this session is closed. So here we can see an example of that client, again, sending a SYN message to the server. Only in this case, the server is sending back a reset. Now the client doesn't really know what's going on in this case. So he says, wait a second, let me retry that. I need to send a SYN message. I need to establish a three-way handshake with you. And another reset is sent back. Again, we retry again, and another reset is sent back. What's happening here? Well, oftentimes this is something that we see when the port is closed. So in other words, if we were trying to make a connection on TCP port 80, but that server is not listening on TCP port 80, it'll get a reset coming back saying, hey, reset that connection. I'm not listening on that port. But you see, if an attacker takes advantage of this method, then he could spoof the server and send reset messages back, making it impossible for a client to establish a three-way handshake and thus talk to anybody. So this is a technique that we use in our IPS devices to terminate unwanted sessions. But when it's used by an attacker, it has the potential to cripple network communications. So as a security analyst, we need to be able to spot this activity when we are auditing our network activity.